In this video I want to have a look at some examples of using the trig identities for a variety of reasons. So there we are, we've got the four trig identities there just underneath the title on the screen. And the first thing to say really is just to remember about what an identity means. So you can see underneath my four trig identities I've written a couple of things. X minus 1 all squared equals 4 and x minus 1 all squared equals x squared minus 2x plus 1. The idea of these two things is to illustrate the difference between an equation and an identity. So the left hand one of those, where it's equal to 4, that's an equation. It's true for some values of x, in this case 2, but not for every value of x. So it's true in the case of x being equal to 3 or x being equal to minus 1, but it's not true for any other value of x. The right hand of the two, where I've got x minus 1 all squared being equal to x squared minus 2x plus 1, is an example of an identity. So on the left we've got an equation, on the right we've got an identity. And the right hand side one, the essential difference between the two is that the right hand side one is true for any value of x. Whatever value of x you substitute in on the left hand side and evaluate that, if you substitute the same value of x in on the right hand side and evaluate the right hand side, you'll get the same answer. Essentially, the right hand side is just an algebraic, well, each side is just an algebraic rewriting, reorganization, rearrangement of the other side. They are equivalent to each other, and while we'll often use an equals sign in that sort of way, in the way that we've done, the way that I have done in that example, it would be equally true to replace that equals sign in that one with the 3 lines to make it an identity, as you can see in the identities, the trig identities that I've got at the top of the screen here. This would not be the case for the left hand one. I can't write the 3 lines there. That would be incorrect because it's not true that x minus 1 all squared is the same as 4 for every value of x. So that's just to remind you and illustrate the difference, remind you about and illustrate the difference between an equation and an identity. So there on the top of the screen underneath the title there, we've got our 4 trig identities. So these are true whatever value of theta we choose to substitute in. The identities are true all the time. These trig identities get used in a variety of different situations. They can be used for just sort of algebraic rewriting of things, to write something in a different way, and very often exam questions, for example, just say show that or prove that or something. This expression with some trig in it can be rewritten or is identical to or something, another expression with trig functions in it. But that's a bit of a sort of made up, if you like, reason for wanting to use trig identities. Really, if we're going to be doing anything very useful, in a practical sort of way with trig identities, generally speaking, the most common uses for the trig identities is for solving equations, to help us to solve equations. It might just be that you're faced with an equation that has some trig functions in it, and you can't, and it's not possible to solve it in the form that it is, and so we might be able to use anyway a trig identity to rewrite the expression in a different way, which might allow us to solve the equation. The other common use, apart from solving equations, the most common use I would say, apart from solving equations, is for helping us in doing integration. You will be faced with a lot of integration during year 13 in both maths and further maths, and a lot of it will involve trig functions, not all of it by any stretch of the imagination, but a lot of it will involve trig functions that you need to integrate. And these can be quite tricky, and very often you'll need to use some way of rewriting the expression that you're trying to integrate by applying some trig identities to rewrite the expression in a different way. So those are the most common uses. There are other uses for them as well, obviously. We can inspect, how the behavior of a function if we rewrite it in a different way, or we can do all sorts of things. Simple harmonic motion, for example, will illustrate different things if we take the trig parts of it and write them in different ways, and all sorts of things. But the most common two are for solving equations and for doing integration. I will say at this stage, as we're launching into the business of identities, you will do a lot more of this in your maths lessons as well as in your further maths lessons. And it is something that requires practice. You get better at it the more you practice, because typically what happens is you see patterns and you start to develop a feeling, a sort of gut feeling for what's a good approach in a particular sort of situation. The more of these you do, the better you will get at them. I think that's very true, and so keep going at them. There are some kind of guiding principles, but I'm not going to go into those in this first video. I'll probably go over some of those in a later one when you've started to use them and see how it works. So at the moment I just want to throw at you a few examples just so that you can kind of get a feeling for how these things are used. So I've got a variety of these here and we'll just launch it. So here's my first one. Oops. If I just post this in here. A little bit bigger so we can see it. So there we have an expression, sine theta over 1 plus cot squared theta, and we're asked to simplify it. And fairly obviously in this case we can see straight away that the bottom of that fraction, 1 plus cot squared theta, is one side of one of my trig identities. Oh, I forgot to say, by the way, look at that fourth identity, the one that I'm just about to use here, and just notice this. That's an alternative way, shorthand way. I think it tends to be more commonly used in America, but also in software packages that write maths well. Cosec is often rewritten as CSC, so I just wanted to put that one in there just to, well, I put that in there because I word processed it actually, and it won't allow you to, it doesn't have a cosec function written as cosec, it writes it as CSC. So that's why I put it there really, but also I think it's good that you see that sometimes these things, that's the only one that's rewritten, generally speaking. All the other ones tend to go as they are. I think the idea of it was really so that it keeps it down to 3 letters like all the other ones are 3 letters. So anyway, yes, that was a little aside. Back to my example, my first example here. So I want to simplify this algebraic fraction with trig functions in its sine theta over 1 plus cot squared theta. The denominator of that fraction, 1 plus cot squared theta, is the left-hand side of that fourth identity, and this means that I can just take that expression and keep the sine theta for now, but just instead of the 1 plus cot squared theta on the bottom, I can just have cosec squared theta, like that. I think we can go a bit better than that. Cosec, remember, one of our reciprocal trig functions, cosec being the one that goes with sine theta, if you remember. Cosec theta is the same as 1 over sine theta. So what I've actually got here is sine theta divided by 1 over sine squared theta. So having a cosec squared theta, 1 over sine squared theta on the bottom of the fraction. I'm dividing by a fraction, so I'm multiplying by its reciprocal. The reciprocal of cosec is sine. So actually what we're doing here is we're, instead of dividing by cosec squared theta, we're taking the sine theta on the top and multiplying it by sine squared theta. And so I can simplify that to a final answer of just sine cubed theta. Final answer. Okay, I'm going to stick at that one example on this video because we're up to over 11 minutes on that one already, and I want to keep them under 15. So we'll stop on that one. I'm going to do some more videos of more examples of using trig identities, but the other ones I won't do all that introductory blurb at the beginning, so we'll have more time in the video for looking at examples.